Question 7. A sample of water at 100 degrees Celsius undergoes the following sequential process. Process 1. An amount of thermal energy Q is removed from the water. Process 2. An additional amount of thermal energy Q is removed from the water. In the final equilibrium state after the process 2, half of the water has become ice at 0 degrees Celsius, while the rest remain as water at 0 degrees Celsius. What is the approximate temperature of the sample after process 1? Evaporation can be ignored. Let's visualize this question using some figure. Initially, there's a water with mass m at 100 degrees Celsius. After process 1, Q amount of thermal energy is released, lowering the temperature to some T where we need to find out. Then, after another release of Q in process 2, the temperature becomes 0 degrees Celsius and half m of water freezes. Clearly, in order to find T, we need to express the thermal energy Q in terms of temperature. This can be done if we are given the specific heat capacity and also the latent heat of fusion. To make the water transit from the initial state of 100 degrees Celsius to the final state of 0 degrees Celsius, the water must undergo 2 steps, cooling until reaching 0 degrees Celsius and then freezing. The former step leads to a release of thermal energy which can be expressed by Cm delta T, while the later part is L times m prime, and in this case m prime is just half m because half of the water is becoming ice. After plugging in the values we know, we obtain the Q to be 293,000 m. Notice that this value is smaller than the amount of thermal energy required to lower the temperature all the way to 0 degree. So we can use the same manner to find the temperature after the release of Q thermal energy after process 1, except now we can forget about the latent heat. And this is what the equation looks like. Since the mass m is not 0, we can rule out from both sides, and after some manipulation we can get T to be about 30 degrees Celsius. So the answer is B.